Okay, so here is what we want to prove now. So we have this function f from x to c meromorphic, and this gave us this function f, which is the same thing really, x to c hat, and we took that eta to be f star of dz. Okay, and we want to show that actually degree of, so the theorem that we want to prove is the following. Degree of eta is equal to minus Euler characteristic of x. X. That's what we want to prove. Okay, so the proof is not difficult, but you have to be careful what you're doing at infinity and at non-infinity. So proof now. So degree of divisor of eta so this is essentially, well, this we know what it is, sum of order of eta at various points, p belonging to x. So this is equal to sum at various points on x, order of, I mean, eta was f star of dz, right? Omega is dz, f star of dz. Okay. So now we break the sum into two pieces. That's a crucial step. So break it into two pieces. So this is equal to sum over all p such that f of p is different from infinity. Yeah. Of order of p of f star of omega, f star of dz, plus sum over all points p such that f of p is equal to infinity. Again, same form, order of p of f star of dz. I mean, dz is really, I should write omega, but I mean, that's okay. I mean, this is dz anyhow, so it doesn't matter. So now let's focus on the first sum. So what is the first sum? So let's look at the first sum. Okay, so order of at p of f star of dz is equal to order at p of d of f of s. You see, f star of dz is d of f of s, right? It's d of f of s. Now I'm using s coordinates for x and z coordinate on c hat. But I mean, we know what that form is. This is order p of d of, so this is f prime of s, basically ds. Prime of s ds. Okay. So now this is equal to order of p of f of s minus 1. And this is equal to, by definition, the valuation of f at p minus 1. So the only thing that, this is definition, and the only thing that you have to be careful is why this is equal to that. But notice that we are taking the derivative of the function because we are calculating the pullback of dz, right? We are calculating the pullback of dz, and for this we have to calculate the derivative of this function f of s. So when you take the derivative, the order drops by 1, obviously. It's just, you have function zm, you take derivative is zm minus 1. So the order drops by 1. So the order drops by 1, and then this order, of course, is the evaluation. Okay, if p is not f of p.
So what's s?
What's that?
What's s?
S is a variable on the domain.
So is it a coordinate chart or?
Yeah, it's a coordinate chart, for example, you can assume. I can just write, but I mean, because I wanted to write in a coordinate system, so I feel more comfortable choosing another notation than Z, because Z is for the target.
Okay.
You see, yeah. I mean, this part is quite easy. So as a result, the first sum then is the following. The first sum you get is sum over all p such that f of p is different from infinity. Well, then there is this valuation of f at p minus 1. So this we have to bear in mind for the first sum. Okay. So now let's look at the second sum. The second sum is tricky because we are looking at points P whose image is at infinity. And if the image is infinity, I cannot use this dz because at infinity, this is not the exact, the right form. We have to choose a coordinate chart at infinity and compute f star of, so imagine this is omega, right? Compute the pullback in that appropriate coordinate chart. So let me write it down and then we'll see what's going on. Okay. So if f of p equal to infinity, then we use coordinate charts. I don't know, w equal to 1 over z, or z equal to infinity on c hat. So once you use that coordinate chart, then your expression will be very different. So second sum then turns into something like this. We have got omega. This form is equal to minus dz over z squared around 0 now. Around z equal to 0.
dw over w squared.
I could use that as well, yeah. I just could, yeah, dw over w squared, yeah. I can use that, yeah. W over w squared. But notice that w is f of s, anyhow, whatever you use, right? Okay, so once you do that, then f star of omega. So f star of omega now is equal to minus df of z or w. Oh, I should use s, sorry. Yes, w is f of s divided by f of s squared, yes. Okay. So now you want to compute order of this guy. So what is order of f star of omega at t such that f of p is equal to infinity? We want to compute this order. So I mean,
is it the order of f star omega at p or the order of f of p star? Shouldn't the p come before f?
Oh no. You see, omega is dz. So that's it.
Yeah, but the p is coming after f. Shouldn't p come after odd?
Oh yeah, here, yeah. Of course, yes. Yes, exactly. So this is or p of f star of omega at those points where f of p is equal to infinity. So let me erase everything here so that I can have. Now, how do we compute this? So imagine, so you can do you can easily see what's going on here because if this f of s has some order, so it's locally like s to the n, right? And then the order of this guy is going to be equal to m minus 1 minus 2m. You see, this is because of the order of f of s is m, so locally it looks like z to the power m, and then f of s squared is z to the power 2m. It's in the denominator, you subtract. Here, you're taking one derivative, you subtract by 1. And this is minus m minus 1, I believe.
So
Yes.
that's the multiplicity of,
Pardon me?
and it's the multiplicity of
Yeah.
f of s.
Exactly, or the order, yes. Okay, so then, so second sum, if you add all these things, so the second sum is just equal to sum minus valuation of p of f minus 1 at all points p such that f of p is equal to infinity. So now if you add the two things, first sum plus second sum gives you the number, basically let me write it, sum. So remember we have mu p of f minus 1, p belonging to x. F of p is different from infinity minus sum 2 nu p of f. F of p is equal to infinity. Oh, no. This is over all of them. Yeah, this is the tricky part. Yeah, this is over all now. Yes. So now if you do this calculation, okay, now this we can use by way of previous formula. This is 2g minus 2 plus 2 degree of f. Okay, so that's what we obtained in previous theorem. Obtained using Riemann-Roch, right? This is what we obtained using Riemann-Roch in a previous theorem. I wonder what is the use of this? This is the use of it now. So it comes out like this. But then there is that term minus this term. 2 nu p of f, f of p equal to infinity.
Sorry, I don't follow. The second sum is equal to that.
Sorry,
Is the second sum equal to that, or is the whole thing equal to that?
the sum.
First sum plus second sum.
Yeah. I did something here non-trivial. I warn you, you have to do this. You have to go through this. I don't want to recall the steps because.
No, I follow that. I don't follow.
Oh, here?
Yeah.
Oh, this, if you look at your notes from last lecture, at the end, I derived this formula that this sum is equal to that sum. This expression. This is the content of the last formula. You can check it in your notes. You have it there. Now, what is this? What is this quantity? What is this quantity? Okay, it's not maybe a fair question, but because we covered this result some time ago, I proved that if you have a map from one Riemann surface to another, its degree can be computed at any point. So that degree formula was independent of choice of points. So recall, for any f, this is very general actually, from one Riemann surface compact into holomorphic non-constant function. This quantity that we define, I mean, for any y belonging to y, you see this degree y f, which was sum of valuation at P of F such that F of P is equal to Y. Remember this? This quantity is independent of Y. We proved that. And now here something like that happens. This 2 is a constant. So this is nothing but degree of F. This is just degree of F. So minus 2 degree of F. Fine. The degree of F, negative 2 degree of cancel, and this remains. That's minus order characteristic. So this is a bit tricky. I mean, the trick was to decompose into 2 pieces, and then there is this non-trivial move here, which I invite you to think about it, because the sum was over f of p equal to infinity and f of p not infinity, but now here the sum is different. All p and then f of p equal to infinity. That's the contribution of those ones. I mean, this is something I'll be happy to go through with you, but not on the board. Okay, so now what we proved is the following, which is very interesting result actually. Now let me. So we showed that if, and that's a big if, there exists a non-constant meromorphic function on X, right? If there exists a non-constant meromorphic function on X, then for any meromorphic one form, meromorphic one form, omega on X, degree of omega is not degree, I mean, yeah, degree of divisor of omega, I'm sorry. Degree of divisor of omega is equal to 2g minus, is equal to 2g minus 2, which is negative Euler characteristic of X. Okay. So that's a major result. I mean, but there is a caveat. I mean, so how the proof goes. I mean, we proved this result already for one omega, namely f star of d eta, right? Eta. So I already proved this. Or omega equal to eta, which was d star. What is this? F star of dz. We just use this f. Okay, and now we know that any 2 canonical divisors have the same degree, so we're done. And since any 2 canonical divisors have the same degree, we're done. Because we prove for one canonical divisor, eta, which is a very preferred object. It's a pullback of dz on S2 or C hat under this meromorphic function.
But there may not be any non-constant meromorphic function.
Yes. So this is the issue now. In fact, there is, but that result is very hard result.
Oh.
So that's where now there is a divide between algebra and algebraic approach and analytic approach happens. So algebraists, for them, there is no problem because they only work with algebraic curves. So there are a lot of meromorphic functions or regular functions for those. But if you are an analyst, you start with an abstract Riemann surface. There is no easy proof of existence, and this is called Riemann existence theorem. So it takes a lot of work to prove that. But for lots of Riemann surfaces that you see in day-to-day in practice, or you see in nature, there are a lot of meromorphic functions on them because they come from equations.
What are the places in nature where you see Riemann surfaces?
Oh, yeah. Where do you see, it's an excellent question. Where do you see in nature Riemann surfaces? I claim Riemann surfaces are everywhere, actually. Show me one.
The cup.
This cup, this chair here, you see. This is actually has 1, 2, 3, 4, 5. If you cut here and close it, has genus 5. This is Riemann surface of genus 5. And if you pinch it a little bit or pressure it, you get another Riemann surface, totally different. If you bend things a little bit, topologically they are the same, but Riemann surfacely they are not the same. They just, so you can take a one of these I don't know, birthday balloons. They turn on. So you can play with it flexibly, and then what you get a curve in the moduli space of Riemann surfaces. Actually, just so they're all different Riemann surfaces. There are so many. The world consists of Riemann surfaces everywhere. You see what I mean? Yeah. So there are a lot of Riemann surfaces. There is no shortage. And another way to see the nature, if nature means algebra, just put your pen on the paper and write down one equation. Any equation you want to write in 2 variables or 3 variables. If you work with 3 variables, you have to be homogeneous. If you work with 2 variables, you can put any stupid polynomial in 2 variables. Ax7y2 plus bxy plus c equal to 0. This gives you a Riemann surface. Anything you can put, any kid, any actually kindergarten kid can write down any Riemann surface. As you move, as you change ABCs, you get a family, 3-parameter family of Riemann surfaces. So algebraically, they are abundant. Physically, they are abundant. In any regard, they are really abundant. Okay, this was a good question. So, other questions? Good or bad, or there's no bad question, by the way. Any question is good. So. Okay, so now let me just take a kind of broader look now what we have. We proved 2 results. I'm gonna record these results in this corner because we're gonna use them. So what we showed is that we proved 2 results. One, what we showed, the first one was that degree of divisor of f is equal to 0 for any f meromorphic. And here is for any omega meromorphic. So basically, have these 2 results in mind now. So we showed that for any meromorphic function, so this we showed several lectures ago, actually, right? So for any meromorphic function, degree of the divisor of the meromorphic function is always 0, independent of f. And for any meromorphic 1,4, the degree of its divisor is, we just proved 2g minus 2, which is minus Euler characteristic of x. Okay. So now, but there is a difference between the two results, you see. There's a difference. What is the difference between the two results? This result is always true, but this result we could prove only if we just assume that there exists a non-zero, non-constant meromorphic function. So that depends on existence of some of it. This result we cannot prove without using that technique actually. So there's a difference between this. I mean, this is anyhow. So. Okay, so now, so here is the question. So basically, given a divisor, B on X. So the main existence question is there a meromorphic function whose divisor is D? So the question is there a meromorphic function F on X such that a divisor of F is equal to D, right? I mean, what does it say? I mean, this is a question that you must have come across in complex analysis, right? In complex analysis, they give you some points as zeros and some orders of zeros and some points as poles, and they ask you, is there a meromorphic function with those points as zeros and those points as poles? This is a very legitimate, valid question, right? That's all. So this question is very easy to solve, to answer on C, because C is not compact in the form that is given. And it's also very easy to answer on Riemann sphere. But above that is an extremely complicated question that we're going to, that actually more or less partially answered by Riemann-Roch theorem. So that's what we're going to do. But now let me go back to this general question. Okay, so you have a general Riemann surface, you have a divisor on it, and the question is there a meromorphic function whose divisor is the given divisor D? So is the answer yes or no? If you are thinking in general, is the answer yes or no?
No.
The way I have written.
In
No.
general, it's no.
What's that?
In general, it's no.
In general, it's no. Why?
Because there will not be any meromorphic functions.
Why? The answer is on the board.
Because the degree of the div of F is 0.
Degree of F? What is degree of F?
So the degree of the divisor of F is 0.
Yeah, so for those divisors that are
Non-zero.
so if the degree of the divisor is not 0, then there is no such function. So we found a necessary condition, right? So of course, necessary condition we found is that degree of D must be equal to 0. So because of a star, right? This is double star because of a star. So you can now modify your question. You say, I have a degree 0 divisor on my Riemann surface. Is there a meromorphic function whose divisor is the given divisor? Yeah?
The degree is 0 divisors.
Sorry?
The divisors of degree 0. Aren't those? Oh wait, hold on. No, never mind. They're not. They need not necessarily be 0 everywhere because they could be.
No, they can be
constant.
cancelled. Yeah, they can be cancelled. Okay. So the answer is yes. So answer is yes. If X is equal to C hat. In other words, I'm saying if you have any degree zero divisor on C hat, then there exists a meromorphic function on C hat. So let me give you a simple example. Let D equal to P minus Q. There are 2 points on C hat, right? Obviously, degree of D is equal to 0. Now I want to write a meromorphic function who has a 0 at P and a pole at Q. That's what it means, right? So degree of F, divisor of F equal to P minus Q means that F has a simple pole, simple 0.
P points.
Sorry?
P and Q are points.
P and Q are points on X, which is C hat in this case.
And at points P and Q, the degree of the divisor is 1.
No, it's 1 minus 1 is 0.
Oh.
That's why, yeah. Okay, so now, so if divisor of F is equal to P minus Q, it means that this is if and only if F has simple pole at P. Simple 0, sorry. And F has a simple pole at Q. And there is no other zeros or poles. That's what we want. So so we want to find a function that has a simple pole at Q and simple pole at 0. What is that? Can you? We know that all meromorphic functions on C hat have to be rational functions. So what is it? This is just Z minus P divided by Z minus Q. That's it. So this is, and in fact, here is a nice exercise. You can check by this working with rational functions that the answer is always yes on. So answer is yes. I already wrote this somewhere. If X is equal to C hat, I'm just writing what I wrote about twice. In other words, take any system of points where the sum of degrees is 0, then there exists a rational function only with those zeros and poles of those given orders. That's quite elementary. But you have to do that, right? But if you go to one genus up, then things start getting extremely complicated. So let's look at one genus up, torus. So this is the question. So the answer is no on X equal to. So the answer is no. No. If genus of X is bigger than equal to 1. For example, you can have this divisor B equal to P minus Q. P is different from Q on C over lambda. This divisor has degree 0, right?
In the case of the Riemann sphere, we didn't specify that P not equal to Q.
What's that?
In the case of the Riemann sphere, we didn't specify that P not equal to Q.
No, P has to be equal, different from Q.
Okay.
If P is equal to Q, then that divisor is 0. 0 divisor is the divisor of the 0 meromorphic function. So the answer is yes, even in that case. So it goes. But that's a good comment, yeah. So we have degree of D is equal to 0 in this case. We are assuming. So the answer is, okay, we will see, we will show. There does not exist a meromorphic F. Such that divisor of F. Meromorphic F on C hat, right? Divisor of F. is equal to P minus Q. I mean, there is a necessary condition in this case, necessary and sufficient condition. This was found by already Abel and all those people. So necessary and sufficient condition. So lift P and Q to C. So we have this quotient map, right? You always have this in mind. C to C over lambda, right? So we have got 2 points, 2 distinct points here, right? Here. And I want to lift it here, right? So I call them P hat, Q hat. The necessary sufficient condition is that P hat minus Q hat should be in the lattice. P hat minus Q hat must belong to lambda. But obviously, no, this is not true, because if P hat minus Q hat belongs to lambda, if you go to the quotient, you're going to get the same points. But we are assuming there are different points. So when you lift it upstairs, the difference is not in the lattice. You see? No. See, this is the lattice. It should be. And the condition, in fact, was found by Abel, and then he solved the problem for in all genus. So,
I don't follow. So P hat.
your P hat and Q hat are 2 representatives of P and Q upstairs, right here.
So why is P hat and Q hat not in the lattice?
Because if they are the differences in the lattice, when you go to the quotient, you're going to get same point, not different points.
Okay.
So there is something called the Abel-Jacobi map. We will study Abel-Jacobi map, and there is a Jacobian of the curve. So the image under the Jacobian has to go to 0. So this is Abel's theorem, but Jacobian in this case is the curve itself. But okay, but this takes maybe a few more lectures. Okay, so already the answer here is negative, and in general is negative. Now we want to start talking about Riemann-Roch. Any questions about this? So now let me write here Riemann-Roch theorem. Okay, so I can actually draw a kind of picture of the story of this course as we started. So we started in lowlands here, right? So then the first summit we had to climb, it was Riemann-Hurwitz. So this was quite it's a beautiful formula. Riemann-Hurwitz is here. And then, okay, so we will prove here somewhere along the road. So for example, residue theorem. And this results, okay, so this results star and double star. And now then there is a very steep ascent. You have to go up. This is the Riemann-Roch. So maybe we have to bring some tools, so some ladders to get there. There's an ice wall here, and there's a may fall. And then there is, after that, there is another summit, which is Abel-Jacobi map. And then there is some Teichmuller theory, another summit. And modular spaces. And then it goes on. I mean, it never ends. It just goes on. But it never ends. But the first thing we have to climb is Riemann-Roch. Okay, so what is Riemann-Roch? So let me tell you. It can be explained quite simple. So Riemann-Roch says that. So Riemann-Roch theorem is the following. It just says for any divisor D on X, and remember X is always a compact Riemann surface for us. For any divisor D on X, dimension of L of D minus dimension of L of D minus K, no, K minus D. K minus D is equal to degree of D minus G plus 1. In other words, people write it like this: L of D, and that's the way I remember always, L of D minus L of K minus D, little l now, not capital L. This is little l, is equal to degree of D minus G plus 1. So so you know all the elements of this statement except what is L of D, yeah.
Okay.
So you can imagine that's a space of functions that's defined, a space of meromorphic function that's defined using the divisor. That's kind of under control by this divisor. So let me define L of D. L of D is the set of all meromorphic functions on X such that divisor of F plus D is bigger than or equal to 0. So I have to tell you what bigger than or equal to 0 means. There is a order relation among divisors. So in general, a divisor D1 is called less than or equal to D2 if what? If D1 of P is less than or equal to D2 of P. So it means that this divisor has to be a positive divisor or non-negative divisor when you add to D. But what does this mean really now? I mean, because this looks like a strange equation, some strange space of functions, but now let me tell you what it means. Okay, so L of D, so the only points that matter are the points where D has poles and zeros. Okay, so now, so let me write it like this: F belonging L of D implies that if P, if D of P is bigger than or equal to 0, then F has a pole, or can have a pole. Let me put it this way. Then F can have a pole at P of order no less than minus less than D of P. You see, because what is this condition? You see, let's look at this condition. Divisor of F P, this is equal to at P is order P of F, right? Plus D of P, we want to be bigger than or equal to 0. So it means that order P of F is bigger than or equal to minus D of P, right? So it means that we can have actually poles, but the poles should not be too bad. They are controlled by, the order is controlled by this dp.
Sorry, how do you get that the divisor of F at P is equal to the order of F at P plus D of P?
But this is the no. This is yes. Okay, so actually what I meant, F belonging to LB, if and only this.
Okay.
For all P, right? Now, if if dp is negative, it goes to the other side. becomes positive, then it means that this f must necessarily have a zero of order at least negative d of p, right? Because we have got here order p of f bigger than or equal to, again, I write the equation minus dp, but this quantity is bigger than or equal to 0. So it means that f has a 0 at p of order at least negative d of p. So you can have higher and higher orders, but
F has a polar.
what's that?
F has a polar.
You see, we divided the discussion into two parts. This is one part, and this is another part. Yeah, this is when no, okay. This is this part. Yeah, right. This is if dp is negative, and in this case, if dp is positive. Yeah. Now, okay, but you remember, but you see that in the definition, I put dimension. So it means that this, okay, I mean, so let me write it. I mean, it's clear that, let me put it like this, easy to see that. I mean, this L of D is a vector space. Because if you have two conditions like this, you add them, you're going to get a vector space. So it's closed under addition and scalar multiplication. So vector space problem is not a problem. But the question is why this is a finite dimensional vector space? Because I put dimension. So that takes some ideas to prove. It's not easy, but we'll prove it on Thursday.
So div f plus d is greater than or equal to 0, that's for all points in X.
The fact that what?
The fact that if little f belongs to L of d,
Mhm.
the divisor of f plus d is greater than or equal to 0.
Exactly.
That holds true for that's a statement about all the points in X. Right?
Exactly. As about all points, yeah.
But this statement about zeros and poles is at a specific point P.
Yeah, these are points. I'm saying points that are dp positive and negative behave differently, control the function differently. Of course, if dp is 0, then there is this just means that this guy has to be the order has to be positive. It means it has to be regular at all other points.
That statement is only about the sum of the order of f at all little p's.
This one?
Yeah.
This is the definition.
Yeah.
Yeah.
That's a statement about the behavior of little f across X.
Exactly. At all points P, this holds.
Yeah, but you're breaking that down into behavior of f at specific points. I don't
Yes.
see how it happens.
Nothing is happening. I'm just writing this at all points P, and then I look at if dp is negative or positive. It has different meanings at different points. One of them controls the zeros, the other one.
Div of f at a specific point P.
No. This is the condition for divisors. Okay, I will explain after the class. Stay after the excellent. That's very easy to explain. Yeah. Okay, so this is what we will prove, and now, in fact, understanding this condition is not so straightforward, because you could say you can define many other types of spaces of meromorphic functions using this divisor. Why this particular one was chosen? Well, to understand that, I think I will have a time. I will show that actually divisors are nothing but line bundles, holomorphic line bundles on the Riemann surface. And this L of D basically is the space of meromorphic, is the space of holomorphic sections of that line bundle, which is finite dimension. So that's the more modern theory, which is completely alien to Riemann. If you told this to Riemann, he said, okay, give me a day to think about it. Maybe tomorrow he would come and prove a theorem about it. But it would be completely alien concept to him. They did not think about line bundles. or vector bundles. They were thinking about this, which is a very, very valid point of view also, because these are zeros and poles, control zero, and that's what they were interested in. So we will get to that, and okay, so we'll start climbing Mount Everest Thursday. Okay. Bring some good gears. Yeah. Okay.